Okay, so hi everyone. Thank you for joining us. It is a pleasure to present this new cosmology seminar. Today we have Professor Nelson Padilla from Universidad Católica de Chile. Nelson holds a PhD from Universidad Nacional de Córdoba in Argentina, and his research interests are galaxy and structure formation in the universe. Today, Nelson is presenting black holes as dark matter field generators. So thank you, Nelson, for accepting the invitation, and you're free to start.
Thank you very much, Daniela, and the group. So what I wanted to talk about today is some, some new work that we've been doing with my group at Universidad Católica, which is composed here by Joaquín Sureda, who's a master's student who's finishing now, two postdocs, Juan Magaña and Marcos San Martin, and also with my colleague Ignacio Baraya, who's recently moved to the north, to UAP, and also with Marcelo Rubio and Federico Stasisin from an institute in Córdoba, the Yate Institute, which is actually where I'm spending my sabbatical year, sort of remotely, but still. So, right. So yes, I want to talk about this, black holes as dark matter and field generators. And to do that, I will first go through, the motivation is basically that we want to check whether primordial black holes can make up the dark matter, right? And what type of mass distributions they can have if they form very early in the universe, right? The history of the universe. Then I will show two applications. One, the effect on large-scale structure, and also using these black holes, primordial black holes, to generate the cosmic magnetic field seeds at early redshifts, but not so early, around redshift 20, for example. And then talk about some work that we are starting right now, which may be interesting to you guys. So let's start. Right, so we have evidence that there is dark matter. I mean, if we want gravity to follow general relativity, we need dark matter because we have flat rotation curves, we have bullet type clusters, which also point to dark matter, and the amount of structure that we see in the real universe. This is a spatial distribution of galaxies from the Sun Digital Sky Survey. Can be compared, the way that the galaxies cluster can be compared to models with different amounts of matter. And here on the right, you have tiny and low resolution servo stamps of the structure that you obtain when you put 4 times more mass than you have, 5 times more mass than you have in baryons, or 10 times more mass than you have in baryons. And the thing is that when you put 5 times more, then you get structures that, believe me, are statistically compatible with what you see in the distribution of galaxies. So we do need to have 5 times more mass. So 80% of the mass needs to be in such a way that it doesn't form stars, and that's difficult to do. So it needs to be in some exotic type of matter, right? And one option for this dark matter course comes from particle physics. There are candidates, for example, from supersymmetry that have the interesting quality that they would decouple from the rest of the relativistic species in the early universe in such a way that they could actually conform this matter that is missing. So it's really, really compelling. But of course, there's still no proof that that is the nature of dark matter. And a few years ago, LIGO detected gravitational waves that come from the merger of objects that have masses that are, that make them black holes. They don't have, these are black hole mergers, which don't produce electromagnetic emission when they collide. They only produce gravitational waves and, of course, a remnant after the merger. But the inferred masses are such that they it's difficult that they come from the death of stars, right? They are around the 20 to 100 solar mass range, and those black holes are too massive to come from the death of stars. And so one possibility for the black holes that LIGO is detecting, or black holes that form part of those mergers, is that they are not from stellar origin, but they have rather formed very early in the history of the universe, right after the Big Bang. And of course, Gonzalo's working on this, and Spiros and other people in the audience. So they know more about the exact way in which these black holes would form. Right, but there's a lot of work on this. The question is, if primordial black holes could be the dark matter, then there should be some consequences in the observables that we can obtain from different sources, right? As a matter of fact, primordial black holes were considered candidates for dark matter, but there was this huge study of weak gravitational lensing or microlensing in looking at stars of the bulge of the Milky Way that was carried out during several years. And they basically ruled out that 100% of dark matter could be in primordial black holes. But the range that was constrained was a range of masses that's relatively narrow, right? And it has been revised and so on. But just to give you an idea, this plot on the right, extracted from Carr et al. 2020, shows the mass of the primordial black holes on the x-axis. In the bottom x-axis, it is shown in units of grams, and in the top axis, it is shown in solar masses, right? Everything that you see in purple, it's basically corresponding to measurements with using basically weak lensing, right? So from supernova, from hypersupernova, and this is, for example, from OGLE, which is the updated version of the Macho project from the early 2000s. And what you can see is that along this range from 10 to the minus 10 to roughly, I don't know, 100 or maybe 1,000 solar masses, primordial black holes will be able to form at the most between 1 and 10% of the dark matter. So, okay, a fraction of them could be, right? But then there are other types of measurements. For example, these red measurements are from the effect that the evaporation of these black holes will have on different observables like CMB, for example, right? And there are also constraints on how much the evaporation of black holes would modify the epoch of nucleosynthesis, for example, right? And there are also here in green structures that would be affected by flying primordial black holes through them, which would be, primordial black holes would be very massive, right? So 10 to the 10 solar mass black holes. So this would be very massive objects that would disrupt or heat up dwarfs and change the large scale structure and so on, right? So there are two allowed ranges here. One is on this region, which are shown on with dashed lines, that could still allow black holes to form all of the dark matter, because these are still sort of disputed. They're not completely safe or certain, right? And in here, there's also a region where there's a little bit of a dispute. Okay, so one thing to note, though, is that all these constraints consider that all of the dark matter is in objects of a single mass. So this is what people call a monochromatic mass distribution, because it's a single mass, a single color, right? So to speak. And you'll see a lot of EMDs in the talk, which refer to these monochromatic distributions here. So aside from a distribution that is completely monochromatic, one could also think that in a plot that shows abundance as a function of mass, you could have extended distributions, right? And those type of distributions will be referred to with EMD for extended mass distributions in the text. So say extended mass distributions. And in which cases could you expect to have extended mass distributions? So this is what my student Joaquin Sureda looked into, basically. What he tried to do was to use the fluctuations, the linear fluctuations very early in the universe to see what happens if you assume that overdense patches are able to form black holes. And the idea is to see if we can relate this simple idea in linear theory to the actual formation, which would happen, in a very non-linear regime at this time, right? Studies of a non-linear regime, for example, from fully general relativistic simulations, show that in order for an overdense region that's original overdense from the initial conditions from after inflation, for it to form a black hole when it comes into causal contact, you would have to have quite a high overdensity, and the mass of a black hole that would form would be related to the horizon mass at that time. And there's these other values here. This is overdensity. This is a critical density for the physical collapse, a physical value of the overdensity, and a couple of parameters, right? So this parameter from the simulation turns out to be 1, and the density contrast is around 0.3 to 1. So if you think, well, I remember from my undergrad years that the overdensity, the critical overdensity for the collapse of the dark matter halo is 1.7. So 0.3 to 1 is not too bad, right? But this is the overdensity of the whole horizon at the time it becomes causally connected. So it is actually quite a large density contrast, considering that this happens very, very early in the universe when fluctuations are much smaller than that, okay? So what would need to happen is that somehow a linear perturbation becomes non-linear very early on, reaching these very extreme values, right? So if that was the case, then the power spectrum that would provide the statistics for the formation of primordial black holes is the primordial power spectrum, right? Because radiation can only affect the fluctuations once they come into causal contact, and the black hole would form at that point. So radiation would not have enough time to modify the shape of the power spectrum, right? So in this case, if we assume that the linear power spectrum that is related to the actual physical collapse needs to be taken into account when the mode enters the horizon, then the amplitude of the power spectrum also needs to be evaluated at the time the mode enters the horizon, right? So this would be the case where the linear fluctuations are taken at horizon crossing to evaluate whether we consider that a real primordial black hole would have formed related to this linear theory condition, okay? So there are other ways. One could also think of for example, vacuum bubbles that expand and collide at the end of inflation, for example, at the end of reheating, and that gives the conditions for the primordial black holes to form instead of the actual amplitude of the fluctuation of the linear fluctuation, right? If this is the case, then the power spectrum that one could think that one could relate from linear theory to the actual formation of the black holes is again the primordial power spectrum, but with a fixed amplitude rather than with the amplitude as the mode enters the horizon. So this basically gives you two extremes, right? One, you say, because you know that the black hole is forming in the fully nonlinear regime, right? But if you want to relate it to linear theory, you can say, you have the two options. You can take the power spectrum as the mode enters the horizon, or you can take the power spectrum at the fixed conformal time. It is likely that this is something that will be in between, if there is any relation, right? But what Joaquin Sureda is check these two extreme cases, right? And it turns out that it's very nice, and because the continuum range between these two options is very easy to model as well, or at least to interpret what will happen in that case. So this is a cartoon, right? So we have the mass of the primordial black holes on the y-axis. We have a scale factor formation. Look at the numbers, very, very, very early, 10 to the minus 30, to today, a scale factor of 1. And the case when the black holes form as they become causally connected happens at later times, at larger values of scale factor for larger masses on primordial black holes, whereas for fixed conformal time linear formation, right, you would take at least that the conditions are set for the formation of black holes at a single time, right? There are a few limits. If you want this to happen, then and you assume a typical end of inflation for then the minimum mass of the horizon crossing needs to be at least 10 to the minus 25 solar masses. That would evaporate by today, but it could still exist. It could still exist early in the universe. And if you allow 60 foldings, for example, you could have black holes that are 10 to the 20 times the horizon mass today. So it's just an academic exercise to see what is the largest that you could form that way. Okay. Right. So okay. So we're saying we are going to take the most widest range of assumptions that will relate the linear theory to the collapse of black holes. Right. That's what we're trying to do here. So what is used in this case is Press-Schechter theory, right? So what Press-Schechter assumes is that only fluctuations that are above a certain threshold will lead to collapse in some way, right? In the case of halos, the physical formation process is perfectly understood. In the case of primordial black holes, the physical formation of the black hole is instantaneous, or rather almost instantaneous, but it is not clear why that nonlinear condition would be satisfied, right? So there's not there is no clear model as in the case of halos. That's why we need all this freedom, right? So what we do is we take the Shechtman-Dorman approach, which is correcting slightly the Press-Schechter case. We simplify the calculations using top-hat window functions in k-space. We allow the primordial power spectrum, which is simply k to the spectral index, which for Planck is 0.96, right? But at some pivot wave number, we allow the index to become blue, right? To basically increase the amplitude for higher frequencies. That's why it's called the blue index, right? And you always see MB as the indicator of what is the slope of the power spectrum beyond the pivot wave number, which we take to be 10, just beyond the observable limit today. And of course, what will undergo collapse is not just the mass that is part of the energy density of the universe, and a very, very small part of that. At the time of the formation of the black hole, we assume that the whole Lagrangian region basically turns itself into a black hole, and all of its energy density becomes the mass of the black hole, right? And so there is a lot more energy density than what is available in mass at the time of the formation of the primordial black holes. I mean, the primordial black holes will be all of the mass if we assume that they form all of the dark matter, right? So in that case, of all the energy density of the universe, only the fraction that would lead to having today the exact amount of dark matter that we measure is what will be collapsing at that time, and that is a very small fraction. So this is one of the critics to primordial black holes as dark matter, is that the formation is to be slightly, or depending, it can be very fine-tuned in order for them to to form the dark matter. But there is a fraction of energy that collapses to the black holes because this is very early. Right. So when we do this, when we use Press-Schechter, there is a very important thing to take into account, that there is a meaningful usage of this. And the usage is that the parameters that one ends up adopting for the mass functions can indicate whether there is a relation between the distribution, mass distributions that you obtain and linear theory or not, okay? So for example, I mentioned that every patch that has a linear overdensity that lies above the critical threshold will collapse, right? But since we have this condition that it's very early in the universe and radiation is much more abundant than the mass that should form at that time, then there is a fraction of that should collapse. But that's the other thing we will have to take into account. But the first one is the comparison between this critical overdensity and the typical overdensities at that time. Remember, this is the linear critical overdensity, so this is not 0.321. It's a different value. It can be very small, right? And what we would want, ideally, is that the ratio of the critical density compared to the typical overdensities at the time of collapse is of the order of 1, because this would mean that the distribution of fluctuations is decisive at the time of deciding how many objects will form, okay? Whereas, for example, if a critical density for collapse is 0, very, very, very tiny, much smaller than the typical overdensities, it means that every overdense patch will form, and there's no relation to the amplitude of the patches, of the density of the patches. So then that's not a meaningful way to use Press-Schechter. It also happens in the other case, where the critical density for collapse is much, much, much larger than the typical overdensities, because in this case, the process that will basically decide where, from linear theory, you form a black hole is completely stochastic, because it is extremely unlikely, right, that it will happen. So the extreme peaks will no longer be Gaussian distributed, right?
Nelson, can I ask you here?
Of course.
So here, the typical overdensity, are you thinking about it within a range of scales, or you're thinking about it in the whole range of scales?
So, right. We take the typical overdensities at the median of the distribution, either of the formation time, if we allow the formation time to vary according to the size of the black hole as it becomes in the causal contact, or at the median mass, if we set the conditions for the black hole formation at a single time, right? So it's the average value, right? It's average for the black holes that form. It's because specifically for...
Yeah, no, I was wondering because I could think, okay, this is the typical overdensities within a narrow range of scales. Let's say the power spectrum peaks at some scale, and therefore it occurs to me that perhaps your the first condition you have in the second line will not really be excluded, because this will be the collapse of overdensities in a small range of scales, and I could imagine, okay, that's not really troublesome.
And I mean, this condition here also uses the power spectrum to set the shape of the distribution of masses. But, and you're right, I mean, there will be a range of masses, but they will be entirely determined by the collapse threshold. So it is, to me, this is not as appealing as this case, for example.
Sure.
But that is a good point, though. I mean, this is not as terrible as this. Yeah. Right. In that sense, yes. Yeah.
Okay, thank you.
Well, thank you. That's an interesting comment, by the way. Anyways, So, right, so this is the first thing, right? Linear theory prefers, I mean, personally, I would prefer definitely this, right? The other thing is this terribly small fraction of resulting matter from the formation of these primordial black holes, right? Because what happens is that the fraction that needs to collapse needs to be the ratio of the density of primordial black holes extrapolated at the average time of formation to the total energy density in that moment. And the formation is at very, very early times. So this density is much, much larger than this, several orders of magnitude, right? So the thing is this: if, for example, I put this the other way around. Sorry about this. Let's do this here and this here. Sorry about that. Right. So if, for example, we take that all the patch that is overdense collapses, then not all patches will collapse. Only this fraction of the patches will collapse. And this is a very small fraction. Even though all of them satisfy the condition, then only a very, very small fraction of them collapses. So this process is extremely stochastic, and again, we lose connection to linear theory, right? If, on the other hand, what we have is that of all the patches, I mean, if all the patches that are overdense, they all produce collapse, but only in the central part of the volume that contains this fraction of the mass, then there is a very strong relation to linear theory. So, but of course, in that case, it is almost deterministic. So for sure, there must be something between these two extremes, right? Yeah, sorry, this slide is not done correctly. Apologies for that. So once you take these two things into account, one can look at the resulting mass functions, right? And here on the right, we have primordial black hole mass on the x-axis and the abundance on the y-axis. And we have different cases, right? In the case that we use this Press-Schechter theory for the abundance of primordial black holes using the assumptions that we saw before, we usually get a power law with an exponential drop-off. And the mass of the exponential drop-off is what we call the characteristic mass of m star, right? And this slope you will see represented by m. Here we have different mass functions for different values of the characteristic mass, different values of the blue index, which is how steep the primordial power spectrum becomes, and different cases of whether a fraction of the patches collapses or only the internal part of the patches collapse, right? When only the internal part of the patch collapse, which is a preferred case, then you get these double Schechter things, like these ones here, right? Notice also the range of masses, which is absolutely crazy. We have 10 to the 40 solar masses. But also have a look at these gray lines. This gray line here is 1 divided by the Hubble volume to Z. So it means this is the abundance that an object will have, so that there is only one of them in the entire Hubble volume, right? So when m star is very large, like 10 to the 25, for example, you won't see black holes that are as massive as that within the horizon. You will only see start to see black holes that are very 10 to the 18 solar masses and below, right? Most of the mass will be on these very large primordial black holes. So these mass functions here are extremely unrealistic, right? They cannot be possibly what when you represent the dark matter or this other mass function here, because we know that the dark matter is definitely of much smaller mass than this, right? It has to be, otherwise we wouldn't have halos that contain galaxies and allow them to rotate, or we wouldn't have narrow or yes, like flat ellipsoids of galaxies, because this would heat up that completely, right? The structure will be different and so on. So the models that could be more reasonable are the red ones or the black ones, okay? And we'll see that the only ones that are actually acceptable are the black ones in the end. Right, so if if you allow a blue index that's larger than 1, the mass functions become shallower. Okay, fair enough. And we can, right, well, this is also just an exercise, right? We need to see what is the effect of having these black holes as dark matter on all the observables that I mentioned at the beginning of the talk, right? So one of the observables is exactly the structure of the large-scale structure in the universe, right? So here's the first application. This is a paper that was accepted this week. No, last week, Friday last week, where we look at the effect of the discrete nature of the black holes and the way this produces changes in the gravitational potential, from the time of matter domination in the universe. And this makes the power spectrum of density fluctuations of everything, right, measured by galaxies, for example, to be different, right? It also changes the abundances of dark matter halos and the way in which these dark matter halos cluster as a function of their mass, right? So this is, I'm going to show you a little bit about this. What happens here is, as I mentioned earlier, we have the fact that the universe has an increasing Hubble volume as a function of time. When we go back, for example, here, right? This Hubble volume here, this is 1 over the Hubble volume. So at earlier times, this line is higher, right? So you will see that the amount of black holes that enter the horizon changes as the universe evolves, on the one hand. Then we also have this vertical line here, the mass that evaporates at a given redshift. This line moves to the right. Everything to the left of this line has evaporated by now, right? So these two effects make the amount of mass that you have within the horizon in primordial black holes to evolve with time. In the case when you have an extended distribution of masses, right? So when you do the calculation for 2 different values of the characteristic mass, the characteristic mass of 10 solar masses and 10 to the minus 19 solar masses, you see that the amount of mass as a function of redshift, this is log 1 plus redshift, divided by the amount of mass today can evolve significantly between redshift of 1,000 for decoupling, right, and today. In the case of a very small characteristic mass, the evaporation makes the amount of mass decrease by more than a factor of 2 in this case, right? When you have a large characteristic mass, then the mass density doesn't change significantly. But still, the number density of the black holes can change by more than a factor of 2, even for this characteristic mass that we have here. And of course, the effect is more important for small characteristic masses. But the thing is that there are changes in the number density that you find within a given volume because of the extended nature of the mass functions of primordial black holes. Right. So why does this matter? And it matters because the noise in the number density also induces a noise in the matter density that you have in a given patch. I'm sorry, I have something in my nose. And that noise can be represented by just the inverse of the number density, right? So the field that is discrete will show Poisson noise, yes, and that's fine as long as it doesn't change the gravitational potential. But if, for example, we are already in the regime of matter domination, a Poisson fluctuation will be a source for the actual potential, gravitational potential, and that will grow with time. So this is an equation for the growth since equality for the case that we have Poisson fluctuations in the mass. So in this case, then we can calculate what will be the evolved Poisson power spectrum. It takes this shape. It depends on, for example, what is the number density of the objects that comprise a mass at the redshift that the mode enters the horizon. And that will basically mean that this number density evolves with the wave number plus some other function here, right? So the redshift where you calculate the power spectrum is different from the redshift where the mode enters the horizon, and this basically makes quite an interesting effect on the shape of this Poisson power spectrum. And this is an additional noise that is related to the fact that you have an extended mass distribution, right? In any case, the power spectrum of fluctuations that one will find in the CMB would be exactly the same as the lambda CDM power spectrum, because it's Primordial Black Holes are extremely cold dark matter, so this works out pretty well. Just don't cut fluctuations at any mass, at any k value, because Primordial black holes would not have been relativistic at any time, plus the contribution from Poisson here. So what was this other extra term that we had before? The other extra term comes from this equation here. This also a cartoon equation, basically. The fluctuations in the density of mass will come from the fluctuations in the number density of objects multiplied by the average mass of the objects. But it will also have an extra parameter, an extra term, that is the fluctuation of the average mass. In the case of a monochromatic distribution, this is zero because there's no fluctuation on the average mass. The average mass is simply the mass of the monochromatic distribution, right? And you end up with the typical Poisson noise. But in the case where you have an extended distribution, this term can become extremely important, right? And it can be calculated this way here. And when you do the calculations of what is the resulting effect, you find something very surprising. So here we have the power spectrum of density fluctuations at the redshift of the decoupling. So this is all linear theory. So lambda CDM is here in black, and blue are the different Poisson power spectrums with growth since the mode enters the horizon. Since either the growth since the mode enters the horizon during matter domination, right? So we need to look at the blue lines. And I've put here a vertical line at a k of 1, so this is log k, so k of 1 over megaparsec, where one expects not to find differences with lambda CDM, because up to this scale, roughly, we know that lambda CDM is a good fit. So we need the Poisson contribution to be small here, right? And so this is for monochromatic. And on the right, we can have the power spectrum, wave number. We have lambda CDM. See that here lambda CDM breaks, and that's due to the blue index that I put here, 2.5. And we have in dotted lines the resulting Poisson power spectrum for this particular mass function with a characteristic mass of 100 solar masses. And the dashed lines are what happens when you also take into account the effect of the variable average mass within the volumes that correspond to these K wave numbers, because what happens here is basically that the largest black holes are the ones that can show or not within the volume, and that can increase the noise by, for example, in this case, 4 orders of magnitude. It's quite impressive. And see the richness of the information that is in the Poisson noise, right? Poisson noise is usually just a flat line. In this case, it can be very different from simply 1 over n because of the different factors that I mentioned earlier. Right, and in this case, again, we want to see the blue line compared to lambda CDM and make sure that it's not important, right? That it doesn't change the shape of the power spectrum on scales that are observable either at low redshift or very high redshift, right? So what else can we do now that we have the actual distribution? I mean, the power spectrum of the mass distribution when the dark matter is in the shape in the form of primordial black holes. We can calculate other things just using linear theory, and it's important to mention that it is just using linear theory because our approximation is for linear theory only. And luckily, one can again take Press-Schechter, but this time not for primordial black holes, use it for the formation of structures at late times, right? For the formation of dark matter halos where galaxies form and evolve, right? So that requires as an input the total power spectrum of density fluctuations, which we take as lambda CDM plus the Poisson contribution from primordial black holes. And in that case, the distributions of dark matter halo masses, these are halo masses, which is the typical one, extending it down to 10 to the 8 solar masses and up to 10 to the 16, the super large clusters, right? We can compare that to actual observations. Here, the little dots with arrow bars from Sloan. We can see, for example, that the lambda CDM case, which can be seen right here in black and below the red line, is a reasonable match to the observations. Observations are quite noisy, quite biased. It's actually difficult to make a comparison and to do cosmology with this function, but it's still illustrative to see that the agreement is reasonable, right? It's not particularly bad. And this case, the top case, is for monochromatic distributions. And you see that when you put, for example, all the dark matter in primordial black holes of 10 to the 9 solar masses, the expected distribution is the green one, and it is completely off compared to the observations. So one can actually use this to put constraints on the possibility that dark matter is in primordial black holes of, for example, 10 to the 9, 10 to the 6, or 10 to the 3 solar masses, right? And down here we have the comparison for extended distributions. If you put, for example, an extreme case with a characteristic mass of 10 to the 7 solar masses, it also is completely way off from the observations. This is for the abundance of dark matter halos. On the right, we have how more strongly is the clustering of halos of different mass. So the bias is what is the ratio of the amplitude of the power spectrum measured from halos compared to the power spectrum of the mass in the universe, right? So if it is higher than 1, it means that the amplitude of the power spectrum is higher. That's reasonable. It comes from Gaussian fluctuations and so on. And again, if you put all the mass in very massive primordial black holes of a single mass, then everything is basically Poisson noise, and there is no clustering, right? There's less clustering than the expected clustering in the mass for lambda CDM case. And the same happens for extended distributions. And again, you can only have at most 10 to the 3 solar mass, characteristic mass, or monochromatic masses, and still match quite well the observed clustering of dark matter halos. So this basically rules out very easily the possibility of having primordial black holes as dark matter that are very massive, right? Very massive black holes. So we apply constraints then to the possibility that these black holes are dark matter. We ask a 10% change in the lambda CDM power spectrum at k of 1 over megaparsecs. And we also check that the halo mass function and bias are not far off from the lambda CDM case or from the measured case, right? And for monochromatic distributions, as expected, this basically rules out that the fraction of primordial black holes as dark matter is 1 for masses that are above 10 to the 4 solar masses, roughly, for this solid blue line. Here are all the other constraints of this region. So we're simply adding another line. Of course, at some point, this is a linear approximation. So the case of using the power spectrum continues down, but it actually breaks. And that is better shown here when we look at the constraints from the halo mass function and from the clustering of halos, right? Which also gives consistent results from assuming a 10% departure from lambda CDM in the power spectrum at a nonlinear K. Right, and it's also quite consistent with this large-scale structure constraint from Carr et al. 2018. That's another fact. The thing that was not considered before was what are the constraints on extended distributions from Press-Schechter, and what we find in this particular case are these red solid lines. Those red solid lines are the maximum value of m star as a function of the blue index, or the characteristic as a function of the blue index, where dark matter can be in the shape of primordial black holes in full, right? And the green regions are the regions from Joaquin's paper that he obtained by using a formalism to adapt the monochromatic constraints for extended distributions. So basically, using the power spectrum, the halo abundances, and the halo clustering help to rule out these extremely high M star regions that were still viable when just using all the published monochromatic constraints for extended distributions. And one really, really interesting thing is that this red line here is showing approximately the region of the plot where the critical density for collapse, linear critical density for collapse, is of the order of the typical overdensities for these mass distributions. And that means that of these three regions, these surviving regions here, the ones that have a characteristic mass of roughly 10 to the 2 solar masses are very close to having a critical linear overdensity for collapse similar to the typical overdensities at that time. So not only these regions provide 10 to the 9 black holes of the mass that LIGO detects, it is also physically sensible. So I've taken a lot of time on this one. Let me briefly go on the second application, which is a paper by Ignacio Araya, Marcelo Rubio, and the rest of the group. And the idea here is that if we can produce magnetic fields around primordial black holes or primordial black holes that are magnetically charged, can we produce the seeds needed for the magnetic field that we observe in the universe? So there are two ways that we could think of to have a magnetic field associated to each black hole. One is that there's a Biermann Battery process where baryons are accreted by each primordial black hole starting the onset of matter domination. And in that case, if we assume that the black holes are maximally rotating, where is that? It's already assumed here. So they have a maximum spin. They can produce a dipole of maximum amplitude, right? A magnetic dipole. And then there's this other mechanism, which is simply assume that there are magnetic monopoles that are basically accreted at the time that the primordial black hole forms, right? So, of course, monopoles can either be positive or negative, but the fact that there is a certain number of monopoles, positive monopoles, that will be accreted, it means that there could be also a Poisson noise on the number of monopoles, of positive monopoles that the black hole would accrete, and conversely, there would also be Poisson noise on the number of negative monopoles that the black hole would accrete. In the end, the net charge that will be obtained this way is basically proportional. It basically goes as the square root of the number of monopoles, right? So in this case, we would have a magnetic field of the Coulomb form, and the amplitude of the power spectrum, the amplitude of the magnetic field will be proportional by this constant k to the square root of the mass, right? And it will drop off as r squared, right? This constant is related to the charge, to the permissivity of the magnetic permissivity of the medium, the charge of the monopole, and it will be related to the number density of monopoles divided by the mass density in primordial black holes. this is really nice because if we want to have a certain amplitude of the magnetic field, then we will require a number density of monopoles, right? So to do that, we need to first we need to obtain what is the average amplitude of the magnetic field on different scales, right? To do that, what we need to say is that all the fluctuations in the magnetic field should be related to the only fluctuations that we have in the universe, which are the matter fluctuations. So we use the Poisson and lambda CDM power spectrum that results from different monochromatic in green and extended distribution in different colors for the matter power spectrum, and use that as the source that provides the magnetic power spectrum. The magnetic spectrum in the end is related to the mass power spectrum by this function here, which takes into account what type of magnetic field this primordial black holes have. Right? And finally, we obtain this beautiful magnetic power spectra for the case of extended distributions here on the left and the right, and for monochromatic distributions on the bottom panel. These are just magnetic power spectrum. And what we find is that the higher the value of the characteristic mass, the higher the power spectrum is, and the lower the characteristic scale where the maximum of the power spectrum occurs. If you have higher number density, you have higher fluctuations for the magnetic field and higher characteristic wave number. You have higher magnetic fields for magnetic primordial black holes than for Biermann, mostly because Biermann produces dipoles, which fall off more rapidly. And you have larger magnetic fields for extended mass distributions. This is the summary. In order to explain the observed magnetic fields, we need to have seeds of the order of 10 to the minus 30 Gauss at redshift 20. Right? So we require this with monochromatic mass functions, regardless of the mass, and using, for example, the maximum possible abundance of monopoles that would be consistent with what we observe. This is the case of magnetic monopoles in red. We at most get to 10 to the minus 34 Gauss. It's too low, right? And considering primordial black holes of single mass of 10 to the 5, which are ruled out, right? This is a region that could be adopted for monochromatic distributions, and the seed magnetic fields would be too small. Instead, if we use magnetic primordial black holes and assume that they produce the required 10 to the minus 30 Gauss, in the case of magnetic primordial black holes, the resulting omega monopole today would be always very low and lower than the present day bounds for this value. So, right, this of course a very nice result, interesting, and we are also working on other things in progress. We're looking at mergers. Sorry, there's little Spanish here, of binaries using the number of primordial black holes that we have in the we find in the Bondi mass around single primordial black holes of different mass. The Bondi mass will include whatever there is. There are matter baryons. If there are baryons can be used to basically allow two primordial black holes to collapse into one another and spiraling and form, for example, mergers. So that's one thing that we're working on. But since I am definitely out of time, let me show the conclusions. And just quickly, we presented with Joaquin the possibility that we can actually produce extended distributions of the Schechter form that are physically sensible with critical overdensities of the order of the typical overdensities, all linear at the time of collapse, which is very, very interesting. We also were able to study the Poisson noise in the case that it affects gravitational potential, use it to rule out dark matter in primordial black holes that are more massive than 100 solar masses, for example. And finally, we show that magnetic primordial black holes could produce seeds for the observed magnetic fields. So I'm going to stop here. Thank you very much. And I can take questions, more questions.
Thank you, Nelson. Thank you for a very interesting talk. So yeah, we have time for questions. So please go ahead.
I can.
Mhm.
I have some question and some comment. Okay. So I will start with the comment. You showed the constraints for monochromatic mass functions, right? But I mean, when you have polychromatic mass functions, these constraints change dramatically, right?
Actually, not so much. I mean, this figure here, you can still see my screen, right?
Yeah.
So this figure is a constraint for the extended distribution, for the polychromatic ones.
I see.
And all right, so for example, for the case of linear formation and horizon crossing, you're right. The window that was there for monochromatic distributions disappears. But if you take formation related to amplitude of power spectrum at a fixed time, then the monochromatic window is there, right? This is around 10 to the minus what? 10 to the minus 5 to 10 to the minus 11 solar masses is allowed as at 100% level. So it's not strictly one-to-one, but I mean, of course, this means that the characteristic mass lies in this range, but you have a full population of lower mass black holes being there as well, right? Because it's in a very extended distribution, all the way to the evaporated mass today, right? And this window is not there in the monochromatic distributions, but it appears when you adopt an extended distribution. And this is the window that is, it's extremely beautiful because it provides, corresponds to the case where the collapse delta is the typical one in linear theory. Although, from Gonzalo's comment, all the region below would also be reasonable because that's a good point. That's only on a range of scales, but
Right. I mean, you have to be on a range of scales, right? Because I mean, you're talking about small scale, so you have to be sure that you don't affect CMB and stuff like that. So that's not. I mean, you're away from LSS scales. You are in smaller scales, right? So I think that's what Gonzalo meant. That this is not this is a relation that focuses on super small scales relevant for PBH formation.
Yeah. Yes.
And
I mean, one thing that we did not consider is that, I mean, it's actually quite restrictive to just think of the scales where the black holes form, right? We should actually think on all scales, but what are the relevant scales in that case?
Right. But then you would have a power spectrum that has some bump in a range of scales.
Right, but this characteristic over density here is, I mean, all the power spectra that are shown here, the primordial power spectra are always consistent with observations in all the space. Every point is consistent. Yeah. So the Poisson noise coming from matter in primordial black holes basically removes all this upper part. All the solid line up is basically restricted, but all this region is perfectly consistent with observations. Only what we're saying when we compare the linear critical overdensity and typical overdensity at the time of formation is to check whether it makes sense to use Press-Schechter or not.
Right.
Yeah. So go ahead. Sorry.
And when you say linear, you mean that you compute the power spectrum from linear perturbation theory? You compute this magnitude of delta that you have in this denominator from linear perturbation theory?
Yes. Yeah.
Okay.
So we do everything in linear theory because at some point you
want to do analytics. I guess you want to do it analytically, or you don't want to run a huge simulation and see the collapse. I guess yes.
We do, but we haven't done it yet.
Right, I know you can, but
No, we're actually desperate to run simulations, and we're going to start doing it now, I hope.
yeah.
Yes.
And
But I mean, this gives us initial conditions for simulation.
right. And also have a question. Okay, maybe I should ask if anybody else has a question, and then I can ask later. So, fine.
I have a question.
Okay.
These magnetic black holes, I'm referring to the last part of your talk.
Yes.
If they collide, apart from emitting gravity waves, do you have an electromagnetic counterpart?
I don't know. That's a good question.
Or perhaps it's just negligible for the amount of...
Right. So the amount of charge that they have is actually quite small. So compared to their mass, the charge is tiny. And furthermore, Marco, Marco San Martin, he's finishing some calculations showing that all these black holes should be charged electrically as well. So if they spin at all, then they should also produce magnetic fields. So it should actually be quite common that there are magnetic fields associated to the black holes, right?
Yeah.
I mean, this is extremely. I mean, there's no proof that monopoles exist, but we know that electric charge exists. So in that case, it should be commonplace that black holes have magnetic field, a magnetic field at this dipole, but it will be tiny.
Okay.
Yeah.
So these are not. They will not be neutral, and in principle, there could be some additional signal apart from the gravity waves that they emit.
Yeah. Okay. It would be nice to do that calculation, actually. But yeah, so we can actually work out what is a magnetic charge as a function of mass that will correspond to each of the cases of the table down here, right? So because I mean this was just a calculation of the average amplitude of the magnetic field on the scales that are brought by observations. It's not the magnetic field associated to each primordial black hole. But right, yeah. So these are on kiloparsec or megaparsec scale. So it may be much more important when you think of emerging.
Okay, thank you.
So thank you. More questions?
If I may, I would like to ask a question related to the dark matter abundance.
So the dark matter, sorry?
Dark matter abundance.
Oh, yes.
Is it obvious that the dark matter constraint is satisfied? Because when you show, for example, M star versus the blue index,
yes,
if you pick up a value for N, then you know what M star is. And I guess that if you know both of them, you can compute, given the distribution, you can compute the dark matter abundance. So it's not obvious that you obtain the Planck value.
Right. So in this plot, I think you're referring to this plot, right? Where we have N and stuff. So here, every point of this parameter space is basically taken, assuming that all the dark matter, the exact amount that we measured today, is in the form of primordial black holes with these with these different mass functions, right? As you move along the plane, you have different mass functions, but they all would satisfy that today we have all the dark matter in these primordial black holes. Of course, except this gray part where they would have evaporated by now, right? But all the white part of the plot allows to have exactly the amount of dark matter that we have today, except that having dark matter in those primordial black holes basically is ruled out by several observables, right? So in the end, the observable that comes from Poisson noise in the power spectrum is just a red line, right? Everything above the red line is discarded, and everything outside the green regions is taking into account effects on the CMB, effects on nucleosynthesis, weak lensing measurements, modification of the, survivability of dwarfs, and so on.
Okay, thank you very much. I missed that part. It was not clear to me.
Oh, sorry about that. Thanks for asking, though.
Oh, thank you.
I have a question for Nelson.
Yes.
Yes. So I have read some papers about primordial magnetic fields. Is there a possibility that both topics could be like related? Because there's a statement that primordial magnetic fields could solve the H0 tension. So
yeah, I saw that paper. Yes.
Should be there a connection, or this we are talking about magnetic fields that are in different epochs or different magnitudes?
So I'm not really sure actually, because so this will be a way to produce evolving primordial magnetic fields, because they will be associated to primordial black holes, right? So you would always have magnetic fields, especially for the magnetic black holes, right? In that case, you would always have magnetic fields in the universe. And in the case of Biermann, you would have Biermann Battery case, you would have magnetic fields coming from primordial black holes, starting after matter domination onset.
Okay.
There are other ways to produce magnetic fields, of course, which come, for example, from vortices produced in nonlinear evolution, for example, that can also produce primordial magnetic fields. So, but it's not clear whether any of these mechanisms are certain to produce the primordial magnetic fields.
Okay.
So, right. So even the formation of primordial black holes could also produce vortices, because it's very nonlinear, right? And there could be magnetic fields as a result of that. The effect of magnetic fields could induce further vorticity and produce more primordial black holes, and so on. So it could be even a feedback mechanism there, which is interesting. But yeah, so there are different ways.
Okay. Thank you. Walter, have a question?
Yes. Hi. I have a small question regarding about the initial condition that you're using here. So in order to compute this extended mass function, you have to impose a blue tilt in the power spectrum, right?
Yes.
And with that, have you some plan of what could be, for example, the underlying theory under that, or some model from inflation, or?
So we haven't looked at the actual models that will produce that. We know that there is basically a range of possibilities from inflation theory to produce blue indices, and the limit is around a blue index of 4. But I should point out that on this plane here, on the x-axis, you see that the power law index of the mass function moves from a very steep on the left, and it continues. There's a change here, right, which comes from horizon crossing to fixed conformal time, but the change in the slope is continuous. So fixed conformal time could produce reasonable mass functions without the blue index. And if it is not, if it is in the middle of horizon crossing and fixed conformal time, you could also produce acceptable mass functions for the whole of our matter without the blue index. But it's everything is sort of mixed here, whether you put index or when you take the power spectrum at horizon crossing or fixed conformal time.
Yeah, I was mainly going in the direction of if you're considering maybe that you could have non-Gaussian initial conditions due to this power spectrum enhancement, or Because if you have, I had the idea that if you have non-Gaussian initial conditions, then you had to modify the mass function relations, and you will have to modify the computations in that sense.
Yeah.
Or if you're planning to consider something in that direction.
So one thing that, but I mean, we only looked at the power spectrum, right? So if we wanted to look at the effect of having Poisson fluctuations in addition to Gaussian ones, or to use that to put constraints, then we will need to look at the bispectrum, which we haven't done yet. Of course, we're limiting ourselves to linear theory. So I don't know, you know, if it is barely seen in the power spectrum, in the bispectrum, it will be more difficult, but because the amplitude of the Poisson fluctuations is at most of the order of the ones coming from Gaussian fluctuations. Yeah. So, but it's still something that would be nice to do. Yeah. The bispectrum.
Okay, thank you. Yeah, I get it. Thank you.
Okay, so one more question.
Let me switch on my lights because it became too dark here.
Okay, no problem.
I have a related comment on the last discussion with Walter, that, I mean, even if you compute the power spectrum, if you have some non-Gaussian distribution, I guess it will affect also the power spectrum, right? I mean, of course, it will give you a bispectrum, but it will also affect the P of K, I guess.
Yes, yeah, but the Poisson, that, I mean, the Poisson power spectrum is actually the correct calculation of the mean square root of the fluctuations for the Poisson case. So it's just, but only for the power spectrum, and we're ignoring effects on higher order correlations, basically. Power spectrum, higher order. So yeah, we could look at that and compare, for example, to measurements from CMB as well. In the end, I have to say though, that of course the CMB cannot be measured up to the scales that we're assuming that the power spectrum needs to be the same. The actual constraint comes more from the Hale mass function again, because the scales are too small.
Yeah,
but
right.
They're enough. And yeah. Oh, by the way, I clearly forgot to say something that's actually quite interesting. If you allow me, I can abuse of the time you guys are putting into this talk and show that here, the halo mass functions change in quite an interesting way on the range of 10 to the 8 solar masses, right? And those are now being detected in very, very careful studies of strong lenses in clusters of galaxies. So one could actually look at this there.
So Nelson, I guess you consider a blue tilt because you're thinking, okay, on long wavelength, I have the CMB, right? And we know that the amplitude is smaller. But you could still, just for out of curiosity, examine red tilts, and because who knows, maybe there is something weird between the CMB and smaller scales. What would you foresee in that case if you considered red tilt?
So if you let's again concentrate on this plot. So this is the slope of the extended mass function, right? And these are the blue tilts for the horizon crossing case, and they start from 1 to 4 roughly. And for fixed conformal time, they go from 1 to 4 here, right? So a red tilt with formation at fixed conformal time would basically correspond to this plot on the left.
Mm-hmm. Okay.
Right. So if you start looking at the plot left of this line, you can think that this is formation related to linear fluctuations at fixed conformal time with a red tilt. I mean, you know, possibly, right? We need to do a calculation, but it's likely that it will be like that.
I see.
Yeah. And of course, horizon crossing cannot even be used to form black holes without a blue tilt, because a red tilt, like the one we measure, for example, like the red spectrum, it's a red spectrum in the end, what we find from the CMB, doesn't allow the fluctuations to be smaller for larger volumes.
Yeah.
And that basically breaks down the assumption that the way in which Press-Schechter works. So yeah. But we could have a very, very red tilt with fixed conformal time that would still allow you to calculate something.
Yeah. Thank you.
So, well, we are on time. Thank you very much, Nelson. Thank you for the discussion, for your talk. It was very clear. Thank you everyone for coming. So, hope
Thank
to
you. It
see
was
you.
very nice. Thank you for allowing me.
Hope to see you in the future in person.
Around, yes.
Yeah. Bye bye. Thank you very much.
Bye.
Bye everyone. Thank you.
Bye.
Bye bye.